All right, good morning, good afternoon, good evening, good night, depending on when you're watching this video. In this video, I'm going to demonstrate a one-way ANOVA F-test. The one-way ANOVA F-test is used to determine if there is evidence of a difference among three or more population means. So we have studied single sample hypothesis testing where we ask a question about a population mean. Then we have studied two sample hypothesis testing where we compare two population means. And we ask questions like, are they different from each other? Is one larger than the other? Is one smaller than the other? In this illustration, we're asking a general question, is there evidence that three or more means are different? All right, so in the illustration, it says, a clinical study was conducted to see whether an antibody called denosumab is effective in treatment, we'll call it Deno, is effective in treatment of osteoporosis of postmenopausal women. Okay, so there's an article that gives you more details on where the data came from and more details about the study. In essence, postmenopausal women with osteoporosis were randomly assigned into groups that received either a placebo or 6 month regimens of the drug of interest at 14, 60, 100, or 210 milligram dosages. And then we have a set of summary statistics given below. All right, so you can see in this illustration, the way that the data is presented is a table that shows 5 different groups. So we can imagine that each of these groups, so the placebo, the 14, the 60, the 100, and the 210 dosage groups, those are individual groups with their own population mean. So imagine there's a mean for each of the 5 groups. So 5 population means in total. We want to know, and we'll get to it momentarily, is there evidence that those population means are different from each other? Okay. So when we want to compare those 5 population means, so we have 3 or more means, this is where an ANOVA F test is used. Now, before I show you the steps, we have a couple of refresher questions or older style of questions. So the first one, is it an observational study or a designed experiment? This is a designed experiment. Since patients are randomly assigned to dosage groups. Okay, B, what is the factor, or sorry, what is the response variable? The response variable here is the body mass index. Okay, so we are measuring the BMI of women. So this is the response variable. This is the thing that we are reporting. So all of the summary statistics, X bar and S, those are the sample mean and the sample standard deviations for each group in terms of BMI. Okay, so our response variable is the value we are measuring. So this is the body mass index, the BMI. Okay, and then C, what is the factor? The factor is the drug of interest, so the Deno drug. Okay, so this is the variable that we are using to split the groups. And there are 5 levels because we have 5 different dosages, 0, 14, 60, 100, 210. Okay, so the drug is the factor that splits the response variable into groups. Okay. Okay, so at the 10% significance level, is there evidence that a difference exists in the mean BMI for women in the 5 different treatment groups? So this is a standard ANOVA, one-way ANOVA style question. We are looking for evidence of a general difference among 3 or more means. Okay, with ANOVA testing, we don't have to do the assumptions in this course. We are going to assume they are met. They're slightly more complicated than what we have seen before. So I'm going to move forward directly to the hypothesis test. Okay, on step 1, my null hypothesis is that the means are equal. The alternative is that a difference exists. So I'm going to have mu1 equals mu2 equals mu3 equals mu4 equals mu5 versus the alternative, a difference exists. Notice how general the alternative hypothesis is. The null hypothesis is always equivalence of the means. So the null hypothesis will always just be mu1 equals mu2 equals mu3 up to however many means you're testing. The null hypothesis is always just that a difference exists. It's a general alternative. And when we say a difference exists, it could mean that mu1 is different from mu4, or it could mean that mu2 is different from mu5. The alternative does not mean that all of the means are different. It just means that some pair of means in the system are different. Okay, on step 2, we state our significance level. In this particular case, we are using the 10% level. All right, now on step 3, we are going to compute our test statistic. All right, so to compute the F test statistic, the easiest thing to do is use an ANOVA table. So an ANOVA table takes our 3 sources of information, which are the treatment, the error, and the total. We compute the degree of freedom for each. We compute the sum of square for each, the mean square for each, and then the F value. Okay, in this question, we are told sum of square treatment is 98.07661. Okay. And then we are told the sum of square error is 5,586.36. To get the degrees of freedom for the treatment, we take the number of levels and we subtract 1. So there are 5 levels in this problem. So that means the degree of freedom treatment is 4. So number of levels minus 1. To get the degrees of freedom for the total, we take the total number of observations which are in the study. In this study, there are 236 observations. Okay, so if we add the 5 sample sizes together, we get 236. The degree of freedom total is the total sample size minus 1, so 235. The degree of freedom for error is simply the difference between the DF total and the DF treatment. So this is going to be 231. So you can see that these columns here add together. So we can also find the sum of square total by adding the SS treatment to the SS error, and that gives us 5,684.437. To get the mean squares, you take the sum of square and you divide by the associated degree of freedom. So the mean square treatment is 98.07661 over 4. So that gives us 24.51915. And the mean square error is the sum of square error divided by the DF error. So that's 5,586.36 over 231. So that gives us 24.18338. The F value is found by taking the 2 mean squares and dividing them, well, specifically by taking the mean square treatment and dividing by the mean square error. So the F value is 24.51915 divided by 24.18338. So that's 1.014. Okay. And this quantity here is the test statistic. Okay, so the ANOVA table is our tool for summarizing the calculations required to get our test statistic. What we need in the end is the F value. You'll notice that the totals, so the DF total and the sum of square total, they don't actually factor into the calculation of the F value. You can just work out the sum of square treatment and the sum of square error, but it can be helpful to compute the DF total to get the DF error, for example. All right, now that we have our test statistic, we just have to perform our hypothesis tests. So we can take either, or we have to look for information. So we can take the critical value approach, or we can take the p-value approach. If we take the critical value approach, our first degree of freedom, we'll call this df1, is the df for the treatment. So this is going to be 4. Our second degree of freedom, df2, is going to be the df for the error. So that's 231. So we have an f value on 4, 231, and 0.1. Okay. So this is our critical value. All right, so we have to go to our F tables here. When we're working with the F tables, there are 8 different pages. Given the size of this F value, we're most likely going to be using the last page of the F table. Okay, so I'm going to go to page 7 here. So the second last page. So I have 4 degrees of freedom in my numerator slot. So DFN and DF1 are the same thing. And then I have 231 degrees of freedom in the second spot. Now you can see the maximum we can get from an F table is 120. So in this case, we're going to have to use 4 and 120 because we can't go any higher than 120. All right, so now we're going to match 4, 120, and 0.1, and that gives us 1.99. So the critical value for this test is 1.99. Right. So my critical value is 1.99. And then you can see that the test statistic does not get into the rejection region. So this means that we are not going to reject. All right, if we take the p-value approach, we start by sketching out our F curve. Now we are going to take our test statistic, which is 1.014, right? And we are looking for the area to the right of that value. Remember, again, with F testing, just like chi-square testing, we always work in the skewed tail. So our p-value is the probability that F exceeds 1.014. Now what we do is we go back to our F table. In this case, we're going to take 4 and 120 degrees of freedom because we can't go any higher than 120. And now we're going to look for our value. You can see that our value, 1.014, is smaller than the smallest listed value, which is 1.99. That means the tail area has to be bigger than 0.1. Okay, so since our value is smaller than the smallest listed value, that means that the area to the right has to be bigger than the largest listed value. So here we would say, since this probability here is greater than 0.1, then the p-value is greater than 0.1. All right, so now that we have our critical value and our p-value, if we take the critical value approach, we would say do not reject H0 since test statistic is outside rejection region. And if we take the p-value approach, we would say do not reject H0 since the p-value is greater than alpha. So our p-value is bigger than 0.1. Alpha happens to be 0.1 in this case, so p-value is clearly larger than alpha. All right, and then the last thing we have to do is conclude. So here we would say at the 10% significance level, the data do not provide sufficient evidence to suggest that a difference exists between the mean BMI for across each dosage level. Each dosage level of denosumab. So in this case, we found no evidence of a difference. So we would just say that there's no evidence to suggest that there's a difference in mean BMI across those 5 levels of the drug that was administered. So again, the ANOVA F test, the one-way ANOVA F test, is a test that allows us to check for a difference among 3 or more population means. So this is an extension of a two-tailed, two-sample hypothesis test. If you have any questions, please let me know.